And this is the third video for Career Days, Advanced Algebra 2. I wanted to run through this practice problem because it's a bit unusual compared to the others. What we have is a polynomial that's not equal to 0 at the beginning, but we can easily make it equal to 0 if we add 36 to both sides. And what that will leave me with is x to the fourth power minus 13x squared plus 36, and that has to be equal to 0. You may not recognize it, but this is a factorable trinomial. We can turn it into two binomials here. We'll still follow the same process that we have before, where I'm looking for a pair of integers that multiply to equal 36, but add to equal negative 13. The only thing that we have to be careful of is that our leading coefficients are going to be an x squared inside each binomial, because it's an x squared times an x squared that would equal x to the fourth power. So let's think about a pair of numbers that multiply together to equal 36 but add to equal negative 13. Well, that's going to be the numbers 9 and 4. And if we use negative 9 and negative 4, that's what gets us down to the negative 13. Well, interestingly enough, we have a pair of factors that come from each of those binomials as well, because they are a difference of two squares. So we have an x plus 2, an x minus 2, an x plus 3, and an x minus 3. So what this tells me is that there are zeros at both a negative 2 and a positive 2. So I'm going to abbreviate that like this: x equals plus or minus 2. And same thing with the x's. We have a negative 3 and a positive 3. So we'll call this x equals plus or minus 3. That's where our zeros will occur. And when it comes to sketching the graph, we should recognize that each of these factors have what we call an odd multiplicity. The power that's assumed with each of these binomials is a 1. So we know that at each of these zeros, the graph will cross at each of these zeros. They're not going to touch and turn away, but it's actually going to cross. Now, we also know by the leading behavior of this, the leading coefficient tells us about the end behavior. The tails will both be pointing up because it's a positive leading coefficient with an odd degree. So I know the tails have to point up like this. And the only way for us to get through each of these four zeros and come out the other side following that end behavior means that the graph has to come down, curve back up, curve down again, and then back up to form a nice W-looking graph. Now, if that's a sketch that we think this will look like, let's verify that with the graphing calculator. And again, while it's a bit exaggerated here, let me see if I can zoom back out. There's that W shape. Again, a bit exaggerated. I had no way of really knowing that by looking at only the zeros, but we do get that shape. It's that W-looking graph that we expected to see. So I think we've done a fine job there. Here's another example. This one is a 4-term polynomial that should be factored by grouping. So I'll pause the recording, and I encourage you to pause the video and complete this factoring on your own. We'll compare results. Now, you probably didn't get too far with that, and you should have recognized that we actually run into a problem if we try factoring this by grouping. We can group the first two terms and the last two terms and find a GCF for each, but unfortunately, since the result of this binomial doesn't match, we can't really continue forward with this method at all. So since that doesn't get us anywhere, we might just scrap that approach and consider solving this by graphing only. So let me eliminate these those brackets there, and then let's consider what we can do to solve this by graphing. What we have to do is place this equation without the 0 into a graphing tool, and we're again going to look for where that graph crosses the x-axis. That's what would allow us to find our zeros. Now, because the degree is 3, we can have at most 3 zeros, and we can have as few as 1. The graph has to cross the x-axis in at least one spot because the end behavior of this polynomial, it behaves like this. It's pointing up and pointing down with our tails. So there has to be at least 1. There could be 2. There could be 3 zeros. Let's go to the graphing calculator and figure this one out. And here's a picture of that graph. We have x cubed minus 9x squared plus 27x plus 27. And you can see that the graph does produce the end behavior that we expected. However, what's a bit unexpected is that this curve, this turn, or this snake part of the graph occurs way up in the air. It's way above the x-axis. And if we want to find where the 0 occurs, we have to scroll down and almost out of view in order to see that. Now I'll use the zoom feature to zoom in at this point. This is about where that x value occurs, but you'll notice it's very hard to read because it's not crossing at any even mark. We can't just count that position. So what we'll have to do is use the Analyze Graph command. So I pressed Menu, chose option 6, and we'll switch to our 0 calculator here, option 1. So I'll pick a spot somewhere to the left of where that 0 occurs, and then I'll pick a spot somewhere to the right, and this gives me a decimal result, an approximate location for the 0 of this graph. We have a 0 at negative 0.78, and there's only one of them here, 0.78 negative. So that's our solution. We had no way of finding that by factoring. There is no factor by grouping method that works. There's no GCF common to all 4 of these terms. The algebraic method to solve this is really quite tricky. It involves a lot of extra work that we're not prepared to cover in this Algebra 2 class. So we resorted to solving it by graphing. And if we looked at the graph, we saw that there was a 0 here at negative 0.78. And the rest of the graph behaved something like this. The end behavior pointed downward to the left. It had this curve somewhere up here, and the rest of the tail pointed up and to the right. So that's a good sketch for this graph. Let's try this last example. We again have a 4-term polynomial, but I noticed before I try factor by grouping that there is a GCF. There is a greatest common factor for all of these terms, and I'm going to call that a negative 2 because I can divide the first term by negative 2 and I'll be left with x cubed. I can divide the second term by negative 2 and I'll be left with 6x squared. The third term would leave us with negative 15x, and the last term would be a negative 100. Let's see if that gets us anywhere. We now have a 4-term polynomial that should be factored by grouping if possible. So we have the first 2 terms here and the second 2 terms here. They're inside a grouping symbol as it sits. So we have negative 2, and this leaves us with an x squared times x plus 6. Looks like the GCF for negative 15 and negative 100 is only negative 5. So if I factored out a negative 5, that would leave me with 3x plus 20. And we again, we kind of run into that same problem we had with that last example. These 2 terms don't match, so we cannot continue to factor by grouping. And again, unfortunately, it looks like we're stuck. We'll have to refer to solving this with the graphing calculator. So I'm going to graph this original equation as it was given to us, and we'll see where the zeros exist there. Again, this is an odd exponent, so I know the end behavior this time is going to point like this, up and to the left and down and to the right because of the negative leading coefficient. And since it's odd, I know I have at least one x value that'll produce a 0. We can have as many as 3. So let's see what the graph tells us. And here's the graph that we get in our standard view. And it looks like we have 1, 0, but I'm not sure if that's the only one. So it would be a good idea to zoom out and see if there's any other behavior that we can recognize on this graph. So here we go, zooming way out. There's something interesting that happened here. It looked like it started to curve again. So let's zoom in on this feature. Yep, there's the turn that we expected to see since this was a cubic graph. but at least none of the turns occur near that near the x-axis, so there's no more zeros. We only have the 1 0, and that occurs way down here. Now we can analyze this graph and calculate that 0. So I'm picking a spot somewhere to the left of where I think that 0 occurs and somewhere to the right, and that looks like we have an x value of 5.33. If your calculator produces a result like this, you can ignore this number. Sometimes based on the computer's algorithm or its method to calculate the zeros, we get a number very, very, very close to 0, and that allows us to estimate where the 0 occurs. If we were to expand this, which is scientific notation, negative 5.82 times 10 to the negative 11th power, that means we need to move this decimal point here between the 5 and the 8, move that to the left 11 positions, and that tells us what we're dealing with for a y value. And that's so close to 0 that we'll assume that this x value for 0 is the solution for the 0 and the solution to this polynomial. So x occurs at positive 5.33. And for a sketch of this graph, well, we saw that it shared the same end behavior that we expected. And it pointed up and to the left, down and to the right. We had an interesting curve up here on the x-axis, but we had the single 0 here at 5.33. Now, to finish out this video, let me remind you about multiplicity. Multiplicity refers to how many times a binomial is a factor of a larger polynomial. So we had some examples of that here. I'll highlight this with purple this time to make it kind of stand out as we go back and review. We didn't have any multiplicities in this example, or at least we had an odd multiplicity because in each of these binomials, those occurred one time. We had an odd multiplicity power of 1. In this case, we had x plus 3 with an even multiplicity and x with an odd multiplicity, and that's what produced our shape like this. With the odd multiplicity of 3, the graph crossed the axis. With an even multiplicity of 2, the graph just touched the x-axis. In this example here, we had an even multiplicity at negative 1/2, and that produced an x-axis or an x value that made a 0 in which we touched the x-axis. Whereas this, we didn't list it, but we had an odd multiplicity and power of 1. That's what allowed our graph to cross the x-axis. In this first example back here, we had, again, an odd multiplicity for each of those zeros, and that's what allowed the graph to cross the x-axis. And we even saw that in our very first example in that last video, an even multiplicity and an odd multiplicity that again produced a graph very similar to this example here. So if I ask you, or if a worksheet asks you to state the multiplicity, just tell me what degree is associated with each of the factors. So again, the degree of these factors here would have been 1, so the multiplicity is 1 for each of those. For the multiplicity of this, we would say it's 2. I'm sorry, this one's 3. Multiplicity is 3 for that example, and the multiplicity is 2 for this example, and had a power of 2, and so on. So I hope that that these videos will help you out with the practice problems. I will post the assignment for career days, and you have the 3 days the rest of this week as well as the weekend to work on them. I'll expect all of the work that I post to be submitted by Monday, by the end of the day, Monday.